Hello everyone, welcome to this event in celebration of yesterday's International Women's Day. Thank you for joining us. It's a pleasure to introduce Bethany Marsh from the University of Leeds, where she is a professor in pure mathematics. She did her PhD in Warwick under the supervision of Roger Carter, and after postdoc positions in Bielefeld and Glasgow, she got her first permanent position in Leicester. Then she moved to Leeds and was then promoted to full professor in 2009. Her research highlights include an EPSRC Leadership Fellowship and an LMS Whitehead Prize. We look forward to your talk. Thank you very much for joining us.
Thank you very much, Sabina. Can everybody hear me okay? Good. It's a delight to be here. I'm very happy to be here and included in the Women's Day. It feels rather wonderful, so thank you so much. Let me start by saying a little bit about that. So yesterday was International Women's Day, and it's a global day celebrating the social, economic, cultural, and political achievements of women. And it's a call to action for accelerating women's equality. That's from the website for International Women's Day. And Stonewall also gives some indication of how they could be celebrated by drawing attention to inequalities faced by lesbians, bi women, and trans people. So yes, it's all about inclusivity. Okay, so the theme for 2022 is break the bias. So it's about imagining a gender equal world, a world free of bias, stereotypes, and discrimination, diverse, equitable, and inclusive, where difference is valued and celebrated, and we can forge women's equality. Yes, so I put a few links here that people might find helpful. Hopefully the slides will be available so you can get hold of those links. So actually there was a letter written yesterday by the presidents of these societies, Ulrika Tillman, Rachel Norman, Sylvia Richardson, Alison Etheridge. They've written an article in the Times Higher Education. Unfortunately, it needs subscription to see it, but they're saying what needs to happen to get equality. Okay, and there's also words of women in mathematics in the time of Corona. So this is a follow-up to the Faces of Women in Mathematics. So it's some videos sharing experiences during the pandemic. I don't know how widely known this is. This is an email list, Women in Pride in Mathematics. So it's news and funding opportunities for women and LGBT+ people working in and studying mathematics. And it's quite a useful list. You get quite a lot of useful information from that. Of course, there's the London Mathematical Society Committee for Women and Diversity in Mathematics. And then this last one is a podcast that I was involved in. I was interviewed by the Isaac Newton Institute, and I was there for a semester. Last semester. They seem to be quite good. They seem to have quite good equality policies. So I was made to feel very well. Okay, so I'd like to start a little bit by talking about my experience. I'm a transgender woman. And for many years, I kept that very quiet, kept it a secret. I didn't feel like I could come out and be myself. I focused a lot on work. I think that was a way of kind of getting about it in a sense. So I'd be working all the time. I would occasionally go to, there were weekends where you could go and sort of a safe space, I guess would be the modern terminology, like the Bowman Society provides such weekends. So that was quite helpful. But eventually I went to therapy to try to sort things out. And I went to therapy really because I thought, well, I'm working too much, I need to change something. But then, of course, it led to other developments. I think quite a key moment was when the therapist said, "Well, you could come to the therapy experiment." And then I realised, well, then I've got a whole evening afterwards. I'm happy myself, and that made a big difference. And it was like, oh, this feels really good. This is rather wonderful. I think I was still a bit afraid about going out, but going out with a friend was very helpful. And then also social groups. So I just went to the choir. I was in an improv group just to test out the water and see what it was like. But actually, that all went very well. So, and I think it was small steps. So rather than just trying to change everything at once, I just changed things when I was ready. So I was still I wasn't changed at work at that point.
Share again.
Okay, so it's small steps. So changing only when I was ready to make those changes, and I think that worked very well. That was where you're dealing with the fear. Just be happy with the way things were going. And I think things have changed. Just having the word trans available makes a big difference. It's oh, there's a word for who I am, who many people are. And there was a trans choir, and they had a sort of series of questions about, might you be interested in coming? And one of the questions they said you might have was, am I trans enough? And their answer was, yes. It's like, you don't have to worry. No, you could just come. Everyone as well. And because this is in the university context. And I think in the university, the networks were very important. There's a women's network, and the LGBT plus network was quite important for me to make contact with other people. And I think, yes, friendship and networking are really key to feeling at home in an academic environment. In fact, that led to interactions with the equality movement. I got involved in a network, and then I went to they would have meetings with people from the equality unit, and I could talk to people there, and they were very approachable and friendly. And of course, that is going to vary depending on which university, but they were approachable and friendly, and then I could find out a bit more about how things would go in university if I was to transition in university. And there was a very supportive person who actually we just met a few times. I think she was actually helping me work out what I wanted to do as well. Okay, so yeah, so communication is very important, and learning about the systems and the process for the university, and has quite a good trans policy, which was very helpful. And the HR representative in the department was also good contact. We knew things about how things were. So in the end, it was like talking to lots of people and finding out how that goes. I attended an event, an LGBT plus event, as myself as Bethany, which was quite an exciting thing. Before I completely come out of work, I just came in for that event. That was a big step as well. And I told close colleagues early on, because I thought they should know what's going on. Before I then emailed around the department. I think the lockdown was a bit helpful, because it meant that the coming out was online at the beginning. So there's quite a big process to then actually carry out the social part of transition. So you've got to tell lots of people, and also within the university, there are many different systems. You have to contact different departments and so on. So there's a lot of administrative things you have to do, and in the wider world as well. I've got a spreadsheet with about 400 rates. This is like all the companies that I dealt with shopping and so on. But each one, it's like transitioning step by step. Each one I did, it was like, that's another step. So it feels good. An interesting thing at the moment is telling publishers. I can actually get my previous papers changed over to my new name, even if they've been published before. Which is quite exciting. It's publisher by publisher, so it will take some time to actually organise it. But that's quite a recent change that's been made. The publishers are introducing those policies. And you can just do it. You don't have to negotiate with your co-authors, for example, and things like that. You might want to let them know. So that is very sensibly organised. And I had a very good response. So when I told colleagues, I had lots of, sort of supportive emails coming back, and people have accepted me as I am, and using pronouns and things like this. So, and I think I feel very privileged. I'm very lucky that it's been like this, and I know that it's not like that for everyone. I mean, it's been hard that I've had to wait a long time, but of course, when I've come out, I was in a permanent position as a professor already, so I think that has made things easier for me. But at the same time, I think the world has changed since I was younger, and I think it's much more acceptable to be a trans person. Society is more accepting of trans people. So, and I think there is just something rather wonderful about being able to be myself in everyday life, and I think it's transformed my life being able to do that. Yes, maybe that's a good point to move on to. Does anybody have any questions about that? Yes, I mean, it's this discussion about it's hard to be harder to be a woman in academia. Is that the case? With that everyone is going to have a different experience. But my experience is that I love being with women. It feels, yes, I just have a really wonderful time. So I encourage everyone to do that. Okay, so let's move on to the mathematical part of the talk. So I want to talk about freeze patterns. Okay, so freeze patterns were introduced, well, in fact, there were some earlier papers of Coxeter, but then the main reference is a paper by Conway and Coxeter from the 1970s. So you may well have come across wallpaper patterns. Freeze patterns, geometric freeze patterns, and you can classify the different symmetries that can come up. So are they symmetric in a horizontal line of reflection, or a vertical line, or under a rotation? So these symmetries are classically classified. Okay, but what Conway and Coxted said was perhaps we could have numbers instead of geometry there. So they looked at patterns of numbers arranged in this kind of way. So you have a row of ones at the top, a row of ones at the bottom, and then positive integers in between. Okay, and the key point is that for every diamond, A, B, C, D, and that, so every diamond like that, A, B, C, D, we have AD minus BC equals 1. Okay, and the height is the number of non-trivial rays. So in this example, there are 4 non-trivial rays. So I haven't put the numbers in. I'll show you how to get the numbers. So this rule looks like SL2. So in other words, it's a you could think of this as a 2 by 2 matrix that's been rotated through 45 degrees, and it has determinant equal to 1. Okay, so they're sometimes called SL2 theorem phase patterns, because you could look at SL2Z, which is the group of invertible 2 by 2 matrices with integer entries. And SL stands for special linear. You've also got the general linear group, which consists of just invertible matrices. So here the determinant has to be equal to 1. Okay, so how could you create a freeze pattern? So you can imagine if you've got the second row, you can then start working out the third row using the diamond rule. So one way of getting a freeze pattern is to say, well, I'm going to start with this as the second row. So we could start with all 2s. Way to play something. Okay, so if we start with a row of 2s, then the next entry below is going to have to be 3, because it's 2 times 2 minus 1 divided by 1. In other words, we want the product of these 2 to be 1 more product of the. So we can work out the entry must be 3. Okay, and then of course that's going to be the same as we work our way along. So we get a row of 3s. Okay, and now you could spot the pattern, because you can see what happens on the next row. So we want 3 times 3 is 9. We want 2 times something to be 1 less than 9. So it has to be 4. Okay, so 3 times 3 minus 1 divided by 2 is 4. So that's what the entry has to be. So we get a whole row of 4s. Okay, but you can see that there is a pattern here, and there's no way this is going to end up with a row of 1s. So the next entry will be 5. Okay, so it's working very nicely. It's a nice freeze, and in the modern times, people are studying these infinite freezes as well. There's some work with Karen Bauer and collaborators. An interesting question there is what the growth is. How fast is it growing? This is quite a nice slow linear growth. So let's try a different initial sequence. So I've just pull out some numbers out of thin air. So this sequence is 7 periodic. So you can see there it starts with 1, 3. So we've got 1, 3 again. So it's just repeating itself to the left and to the right. Okay, so let's do the same thing again. So we've got 1 times 3 there. So we have to put a 2 below to get the entry. Okay, and then the next one will also be 2, because we've got 3 times 1. Okay, but then the next entry we see will be 3. So we've got 1 times 4. Must be 1 more times 3. Okay, so we could start filling in the next row. Okay, and we get a nice third row. Okay, there's a bit of hope here because at least we've still got a 1 on that third row. It hasn't grown quite the same way. Okay, and we go on to the next row. We've got 2 times 2 is 4, so we have to have a 3 below it. Okay, and we can fill in the 4th row. In fact, if you look at that, you see that already sometimes symmetries are starting to appear. It's actually the same as the 3rd row, just shifted along a bit. So nice things like that can start to happen. And if we look at the 4th row, actually it's a shifted version of the 2nd row. Sorry, it's the 5th row. The 5th row is a shifted version of the 2nd row. And if we go one more row down, first row we have a nice sequence of words. So the question is, why did this row work? And can we find other examples? And that's what we looked at. So their answer to this question is that you can use triangulations of polygons to get these numbers. So let's take a heptagon. Heptagons seem to get quite a poor press. You don't seem to see very many in talks. So let's have a heptagon for a change. And for each vertex, we're going to count the number of incident triangles. So for this top vertex here, you've just got 1 triangle. The vertex, but for this one here, you can see we've got 3 triangles. All incident with that. 1, 2. 3 triangles incident with that vertex, so we've put 3 there. And so on. We've got 4 triangles here, all incident with that one. And then we read off the sequence. We have to choose direction. Consistent with that, yes. So I'm reading it off here at least clockwise. So it's 1, 3, 1, 3, 2, 1, 4. And now you see where that 7 periodicity is coming from. You just keep going round and round. You can read off a doubly infinite sequence from them. Okay, so that's just illustrating what's going on. So we've got 1, 3, 1, 3, 2, 1, 4 going around the boundary clockwise, and then I've highlighted the corresponding entries in the frieze. So this gives a way of going from the triangulation of the polygon to, well, to at least a row. Okay, and Oxford and Conway said that, well, this will always work. You'll always get positive integers, and it will always terminate, and you'll get 1s. And in this way, you get a bijection between triangulations of a regular n+3 sided polygon and these patterns. So in this case, the height was 4, and it was a 7-sided polygon. So if the height was 5, the next case up, you'd have to take octagons. And so on. Square. That should be height 1. So you get a very simple frieze pattern. That's almost the simplest you could get. And you see that there are 2 triangulations of a square. So the other one is this one. And there's always this question, what does it mean to be a different triangulation? You could say, well, really, that's the same way. Sometimes that's true. But if you fix the square, then these are different because it's a different diagonal. So that's the point of view we're taking. And in fact, the frieze pattern that you get will look very similar, it would just be a shifted along. So rotating the polygon corresponds to moving the frieze pattern to the left and right. So we've got to regard those as different frieze patterns. You've got a frieze pattern with a marked origin. So this is the beginning of the pattern. So if you regard them as different, that's but if you prefer, you could say triangulation set to rotation and frieze pattern set to shift. And you still get a rotation. But other symmetries as well, you could take up to triangulations up to reflection. And then you have to reflect the frieze pattern. And the other thing that they noticed is that every frieze pattern that you get in this way, right, so every frieze pattern is invariant under a certain glide reflection. So you get something of these geometric symmetries. The glide reflection is always something that occurs in the symmetric situation, in the geometric situation. So the glide reflection, it means you translate across and then reflect. And you can see there, if you look at this triangle, here it's the same as this one, but upside down. That's what it's black lines and everything. That's just going to repeat infinitely often as you go. Yeah, so you can see the 7 periodicity as well. It's the composition of 2 of those glide reflections. So it's like a reflect there, reflect there, it maps as well. That's a shift by n plus 3. Okay, so how many are there? A question that I always love to ask. So how many frieze patterns are there? This is given by the idea by Catalan numbers. So the nth Catalan number is 1 over n plus 1, 2n choose n. So remember, 2n choose n is 2n factorial over n factorial squared. Okay, so then we can divide further by n plus 1. So this is, so you can show that that is in fact always an integer. Okay, and then it's a well-known fact that the number of triangulations of an n plus 3 sided polygon is given by the n plus first. There's this nice, there are 2 books by Stanley, quite authoritative combinatorics books. Encyclopedia. There's quite a lot of information. And this is one of the things that's covered. So we've seen there are 2 frieze patterns of type 1. They're the 2 that we drew here. And they're the 2 triangulations of the square. Okay, and then there are 5 frieze patterns of type 2, and there are 5 triangulations of a pentagon. Essentially, they all look like that. So you could choose one vertex and draw two diagonals, and then you can rotate that 5 times. So it gets more interesting when you go to a hexagon, and then there are 14 different triangulations. For hexagon, you start getting things like you have a triangle in the middle. You can also have things like that, so you start to get different looking bits. So you've got this Catalan sequence. So it begins 1, 1, 2, 5, 14, 132. So it's growing fairly quickly, but it's not ridiculous. And the Catalan sequence is quite an amazing sequence. So the sequence counts many, many different sequences of combinatorial objects. And there's a book by Stanley listing 214 distinct sequences, all counted by Catalan. And sometimes the change from one sequence to another is not large. You think, well, okay, that's a small change, but in some sequences it's actually quite hard to find bijection between the objects counted in one and the objects counted in another. And they are all distinct things. And just to give you a flavor of that, so one of my favorites is the bracketings of a product. So if you've got a product of 4 numbers, say A, B, C, and D, there's 5 distinct ways of bracketing. So, okay, so there are rules. So the rule is the bracketing must tell you completely which ones to multiply first. So of course you could say, well, what about that bracketing? But that doesn't tell you whether to multiply A, B, and C first. So there are 5 ways to bracket that product. So a second one, a different flavor, so just a sequence of integers, A1 up to AN. AI is less than or equal to I. So here, A1 is less than or equal to 1, A2 is less than or equal to 2, and A3 is less than or equal to 3. So positive integers. So you've got those 5 options there. So yes, interesting exercises, find the bijection between those two. Of course, you see there's quite a lot of cases. There are 214 sequences in that book. So you've probably got 214 choose 2 bijections to find. There must be some open problems on those days because there's just so many. Okay, and then you could take n non-intersecting chords between 2 endpoints on a circle. So they're the 5 objects there. Okay, so another way to create a freeze pattern, we focused on taking the top row, second row, but instead you could start with a zigzag of 1. Okay, and you could see what this actually is using the die. That zigzag of 1, so you can again complete the freeze pattern. So first of all, we get a 2 there. Then the product is the horizontal merge product is 1 more than the vertical group. Okay, so then we can move in both directions. We can get a 3. I think you got the idea. There is a typo in the earlier version, but the entries are correct. Okay, so that we get a freeze pattern that way, and that always works. And the corresponding triangulation will always look like some kind of zigzag. setting. So you get only some freeze patterns this way, not all freeze patterns. Okay, but the reason I mentioned this is the fun you could have. Instead of taking ones, you take variables. So for variables x, y, and z, in place of that zigzag. Okay, so then you see we'd have to have, for this entry here, we call it the unknown, u for unknown, I guess. Then we'd have yu must be xz plus 1. So u is xz over y. Okay, so the diamond rule tells us what must go there. Now, if you think about that, what's going to come out of that, in general, it's going to be quotients of polynomials. But there's some magic that's happened here. The denominators are all monomials. They're all just products of variables. But with that rule that we're using, that's not a given. So what actually happens is you do get things in the denominator, but it always cancels out things in the numerator. And so you're just left with the denominator. Okay, so these are known as Laurent polynomials. So they're like normal polynomials, except you're allowed negative powers. So you could think of this is something like y to the minus 1z plus x to the minus 1 plus x to the minus 1, y to the minus 1. So it's just like a normal polynomial in x, y, and z. It's just that we'll have negative powers of variables. Okay, and this is an instance of what's called the Laurent phenomenon, the fact that we get these Laurent polynomials. And this was discovered by Bethany and others in a wider context. So if you take these Laurent polynomials, they generate a cluster algebra of type n. So it's one way of getting to the idea of the cluster algebra. So these were introduced by Bethany and others, Sergei Bowman and these others in 2001. Studied a canonical basis of a point of view. They seem to hit a scene. So they're asked to be quite wide. So when I say generated, I mean you take the so A is the sub-algebra of C x, y, z, or however many variables you have, generated by the entries. So that's the actual cluster. And that means it's the smallest algebra inside CXYZ containing these sections. So it means that the elements of the algebra will be polynomials in these entries. Okay, so you take things like, so it could be y times xz plus y over y cubed times 3, and then you might take 1 plus y over z to the 6 times x times y, and so on. So you add up. So you pretend these are your variables, these entries are variables, and then you take polynomials in there. Okay, and you can think of these as functions on a space. So functions on a geometric object, so it's a way of describing a geometric object. And you can think of them as coming from surfaces. In fact, we've seen something of that because the triangulations of the polygon. In fact, you could take triangulations of a general surface, oriented surface, and there will be a cluster algebra corresponding to that. And we've seen the connection with combinatorics, the Catalan numbers, and there are strong connections to Lie theory. This is the type A situation, so SL appearing earlier. Yes. So right now it becomes a bit funky. So think of the variables as the vertices of a directed graph. So I've just drawn arrows pointing left to right. Okay, and you see there we've got X, Y, and Z. I'm going to ignore the ones for this. So we've just extracted that slice there. So now we've got a directed graph, often referred to as a quiver in this context, because it's a bunch of arrows. So we've got our directed graph, X, Y, and Z. Okay, and it has a source, so it has a vertex. Yes, I should say outwards. Where all the arrows point outwards. Okay, and in cluster algebra theory, you can mutate these quivers into directed graphs by reversing all the arrows. Sorry, by doing a local change at a vertex. Now, if the vertex is a source, actually what happens is simpler description. So you just reverse all the arrows instantly from the source and turn it into a sink. And you put a new function at that vertex. Okay, and that, if you go back to this picture here, you see that this y has been replaced by x plus 1 over y. But in the new perspective, we think of this as that's our original quiver with functions labeling the vertices, and then we've mutated it. We've changed some of the arrows in the quiver, and we've also changed the function. Okay, and the new function, if you think about it, you can see that what we've actually got is x times z, so the endpoints of the arrows coming out from the y multiplied together, and then plus 1 and divided by what was there originally. And that is the mutation for a source. But you can actually extend these rules so that even if it's not a source, there is something rule that's very similar to that. And in particular, if it's a sink, so if we started at this source, we mutated it and we got this quiver, we could then mutate it as x here, and what comes out is this one. So yes, we start with this, we mutate it once and we get that, and if we then mutated x, we'll get that one. Get that one, mutated y, then we get that one. So we keep mutating as we move across using this rule. We're going to cover the whole thing. So, and if you allow mutations of vertices that are not sources or sinks, so you see at this point, at some point we got this quiver where it was linear, and that middle vertex is not a source or sink. We've got an arrow coming in and an arrow coming out, but we could still mutate at it. And in fact, then we get a more complicated quiver, we get a 3 cycle. So this picture is meant to tell you what the whole cluster algebra looks like. And moving through the trees means moving around the boundary of this drawing. These are all sources and sinks of nice linear quivers around the boundary. In fact, there are a few more quivers you can get to, like this three-cycle quiver, where you start mutating non-sources and sinks. This is a famous object known as the icosahedron, and it was introduced by Stusher. And in fact, it links back to the Catalan numbers. The number of vertices are also the Catalan numbers, so we're seeing them in a different way. And you can label the vertices instead of by these quivers, you can label them with bracketings, like the bracketings we saw earlier. So these are the 14 bracketings of 5 letters. And the edges are applications of the associativity rule. So let's zoom in maybe here. So we should be able to see an application of the associativity rule. It might be quite difficult to see it. What's been reassociated there? So let's think of this. The E is outside, so it's not changing. So if you think about this BC, think of that as just one product, one of the 3 things. So we've got A. So we've got A times BC times D. So we could re-bracket that and put the BC next to the A. Yes, it's quite fun. So that we have just applied the standard rule for associativity, and that tells us that these 2 bracketings are the same. So I think it's something we take for granted that if you know that associativity holds for 3 things, A times B times C, you re-bracket it, the 2 answers are the same. We take it for granted that if you bracket longer things, that all the answers will be the same. Associativity is in it. The associahedron is the proof. The fact that this is connected is the proof that that is okay to do that. You can go from any one bracketing to any other by moving around the associahedron, re-bracketing it using associativity every time. And for 4 things, it's just a pentagon. And the 6 letters, it will be a 4-dimensional object. So this is natural geometric structure. So the associahedron plays a role in the study of scattering amplitudes in mathematical physics. So I'm not a physicist, but this is what happens when particles collide. So you've probably heard of Feynman diagrams. It's actually a modern approach to study the same things that Feynman diagrams study. Recommend these sort of diagrams, which tell you what happens when particles collide, like in CERN. And that is the amplitude-hedron, which is really being used in this work in CERN. That's a more complex space arising in the theory of Grassmannians, but it's quite closely related to this association. And what's Grassmannian? It's the space of subspaces of a vector space. So a lot of these ideas, in the end, it's linear algebra. Okay, thank you very much.
Thank you very much. Any questions?
So is there a geometric way to see the 3rd row of your 3s in the triangulation?
Oh, okay, nice question. Okay, so the question is there a geometric way to see the 3rd row of the 3s and of the other rows? In fact, there is. There is a way of it's a theory of perfect matching. There's a follow-up paper. So I can't remember exactly the details, but you have to do some kind of, you have to count the ways of associating triangles to the boundary. So that there is a geometric way, yes. So maybe I can forward the reference to that. Yeah, I can't remember the name of the authors at the moment, but there is a way to get the other entries. Yeah, it's a nice question. Yes, there was another question.
This might be a tough question, but are there sort of different versions of these books starting with different kind of relationships with the diamonds? So you have the kind of these kind of say D one, right? But could you do different relationships?
Yes, no, great question. Thank you. Yes, so the question is, are there other relations you could look at when you're defining a tree? So here we've got the diamond relation. Could we have what else could we do there?
I think you dropped your microphone.
So one example is there are additive freeze patterns where you take instead of having AD is BC plus 1, you have A plus D is B plus C plus 1. And more recently, there's the notion of SLK freeze pattern. So here we could think of this as a 2 by 2 matrix, and the determinant is equal to 1. So an SL3 freeze pattern would mean that whenever you had this situation, you could turn that round and say the determinant of that matrix is equal to 1. So different sort of universal. These are not completely understood yet. It's weird, but I think it's Buran. Sorry, Bauer, Faber, and collaborators. So yes, in fact, that's a nice paper to mention because it's I think that's the paper that came out of the Winnert meeting. So this is women in non-commutative algebra and representation theory, and it's essentially it's a collaborative meeting. So people meet in small groups and work on a paper together, rather than having a series of talks as in the Stanford conference. And I think that's the paper that came out of that meeting. So that's because there's a lot of it's highly collaborative. Sherry Enko, I think. But I know I'm missing some authors. You're quite bad. I can't miss the note. Great. Okay, there we go. Freezes satisfying higher SLK determinants. So the title says it all, because it's exactly what I've just been talking about. Because SLK is these higher dimensional matrices. So it's Karen Bauer, Oliver Faber, Sarah Dutz, Christina Sherry-Enko, and Gordana Todorov. So the area of freezes is an area where there are a lot of very good female researchers working. Yes.
So I have a question on how quick you can get the freeze pattern, because it depends on how many ones you have.
So the question is how quick?
How quick you can complete get the freeze pattern.
Oh, you mean how?
Yeah, how many steps do you need to get all ones in there.
To get the ones at the end, yeah. So if you took so you started with the regular n term, like the heptagon, then it would be n minus 3. There'll be n minus 3 non-trivial rows. So if it has 7 sides, then there'll be 4 non-trivial rows, and then the ones will appear. So if you had a 10-sided polygon, it would come up in 7. There'd be 7 steps before you got back to the row. Does that answer your question?
Yeah.
Okay, great. Thank you. And
If you look at the numbers, you don't have any ones in the second row. I guess
yeah, this is a good question. So another variation. Okay, do you have to have a 1? Okay, sorry, that's your question. Do you have to have a 1 in the second row? I think you do. Yes.
This
This is a triangulation. Yes. In fact, it's called an ear. And a triangulation, yes, great question. Yes. A triangulation must always have a triangle on its boundary. So a vertex on its boundary is with one triangle. Yeah, no, that's questions. Thank you. There's a question at the back. Oh yeah, I like that question. Yeah, okay. So the question is, yeah, how else could you start a freeze pattern? Could you set a Sudoku-like puzzle where you just put some entries in different places? I think that would be quite fun. So I don't think anyone's done that actually. You know that in the triangulation, that what happens is that the diagonals tell you where the ones are. So yes, in theory, if you know where all the ones are, you should be able to fill in the rest. But you might need to use some sort of secret additional information rather than just the diagonal to do that. So I think it's a nice question. Yeah, what would be the minimal? What are the minimal possible sets? What kind of Sudoku puzzles could you set? I don't know the answer. Yes.
Is there some way you can start with like a word
Oh, yeah, that's a good question. Okay, so the question is, could you start with a row of 3s? You know, a different thing at the top instead of a row of 1s. I am aware of a paper where they look at 1s and 0s allowed in the top. In that top row. And I think so, I don't know the answer. If you had a row of 3s, of course you could multiply one of these 3s by 3, but then you lose the A plus D plus C plus 1 rule. I'm not sure if they're actually classified. I don't know. So it's a good variation, interesting variations you can do with these freezes, and I think it's still quite a young field. So there's still quite a lot to discover. Do this again later. Sorry. There's one more question, or are we should be again?
Maybe some of us need a coffee. So Bethany has kindly agreed to share the slides. I think some of us may be interested in some of the links, so I will be sending around the slides to all the registered participants. And let us thank Bethany again. So we have a coffee break. Everyone is invited. There is coffee in the flexible space outside. And we then have a panel discussion at 3:30.